Hello everybody, and welcome to today's chem lesson. In our last lesson, we talked about protons, neutrons, and electrons, and how we can use information given on the periodic table and information written in a specific pattern to determine how many protons, neutrons, and electrons there are in an atom. And we ended the lesson looking at a chart. We ended the lesson looking at this chart. And something that was pointed out was the fact that mass number and atomic mass are two different numbers in almost every situation that we look at them. They're similar, they're close to each other, but they're not always the same, right? They are the same in this one circumstance, but most of the time, they're different. And the question now becomes, why are these two numbers different? Why is the atomic mass a number pulled directly off of the periodic table? Why is this number different than the mass number, which is protons plus neutrons? And today we're going to focus on the difference for this. Right? Why are these numbers close but not quite the same? And the reason for this is the presence of things called isotopes. An isotope is a version of an atom that has a different number of neutrons than another version of that atom. So, for example, carbon has an isotope of 12, an isotope of 13, and an isotope of 14. And if we remember some of the stuff we were talking about in our last video, we'll recognize that these are all carbon, but the mass number is different between them. And if we take a look at how many protons, neutrons, and electrons there are in each of these isotopes here, we'll be one step closer to talking about the difference between mass number versus atomic mass. Thinking back to our last video, we know that this number in the bottom left-hand corner is the atomic number. And we know that the atomic number is equal to the number of protons. So for each of these, there are 6 protons. We remember that this number in the upper left-hand corner is the mass number. And that is equal to the number of protons plus neutrons. So in this first atom, we've got 6 protons and 6 neutrons to make 12 total. Here, 6 plus 7 gives us 13 total. And in our last one, 6 plus 8 gives us 14 total. We also remember that this number in the upper right-hand corner is our charge, which is equal to protons minus electrons. These are all 0 charge, meaning that each of them has 6 electrons. Now, when we look at these 3 different isotopes of carbon, we have an important question to ask ourselves. And that question is, what's the mass of carbon? Here we have 3 different atoms of carbon. The first one weighs 12, the second one weighs 13, the third one weighs 14, but they're all still carbon. So if we want to talk about what is the mass of carbon overall, can we use 12? Can we use 13? Can we use 14? And the answer to that is we actually have to take an average. We need to average the masses together to get the average atomic mass. And this is something I'm going to walk us through in a second, but first, a quick little practice problem for us. Which of these symbols represents atoms that are isotopes of each other? So here, if we're looking for isotopes, we're looking for the same element, but a different number of neutrons. And if we want a different number of neutrons, we're paying attention to the atomic mass, no, the mass number, excuse me. So we need a different mass number. Looking at my choices, I'm looking for the same element. Right, so this one's out. These ones are still in. But I need a different mass number, which eliminates choice 3 and choice 4, because those mass numbers are the same, leaving us with only choice 2 as our acceptable answer. Right, an isotope is an atom of an element, or a pair of atoms of elements that have different mass numbers. Now, back to this idea of average atomic mass. If we've got carbon 12, carbon 13, and carbon 14, and we want the average of these masses, we would just take them, add them up, and divide by 3. Right? So we would get an average mass of 13. Right? 12 plus 13 plus 14 divided by 3. But if we look at the periodic table and we look at the information given to us in the cell for carbon, the average atomic mass for carbon is 12.011, which is not equal to 13. Which means we got to do something more than just average them together. And the thing that's missing is the fact that it's a weighted average. Which means that if there's more of one number, that number gets counted more. For example, if you have a grade of 100 4 times and a 0 1 time, and you average these together, it's not 50. Your average is an 80. Because the other hundreds bring you up. The same is true of the reverse. If I have 4 zeros and 100, my average isn't a 50. It's a 20. Because the other zeros bring you down. Right? It's a weighted average. It matters how many 12s, 13s, and 14s there are. It matters how many zeros and hundreds there are. We care about, are they equally represented? Or is one more prevalent than the others? And so when we try to do this calculation to find the average atomic mass, we're looking at a weight plus how common that mass number is. Right? We need a mass number and how common it is. And there's 2 ways of doing this that are mathematically exactly the same. It just depends on which one you prefer. You can take the mass times the percentage for every isotope and then divide by 100 at the end. Or you can take the mass times the decimal version of that abundance and you don't divide by 100 at the end. Either way, when you plug into the top or the bottom, you're going to get the same answer. There's no difference between using this formula up top or using this formula on the bottom. You're taking a weighted average. So you're taking the mass times the abundance plus the mass times the abundance plus the mass times the abundance, right? Once for every isotope that is listed, and then either you're dividing by 100 or you're using decimals instead of percentages. And we're going to look at that with a couple of examples right now. Here we have two separate problems. And notice they give us exact weights and abundances for each of my isotopes. So if I want to find the average atomic mass of this element, I'm going to plug into my formula. And I can do either 12.00000 times 98.90 plus 13.003355 times 1.10 over 100, or equally viable is saying 12 times 0.9890 plus 13.003355 times 0.0110. So either you're taking the percentages exactly as given and dividing by 100, or you're moving the decimal 2 places and plugging those values into your equation. Either way, no matter which one you choose to use, your answer comes out to be the same number, 12.011. And if we think about this mathematically, it makes a ton of sense. There's 99 12s and 1 13. If we're averaging together a ton of 12s and only 1 13, our average is going to be very, very close to 12. Right? If you have 17 100s and 1 0 on your assignments, your grade is going to be pretty close to 100. You'll have like a 99.5 or a 99.8 because you have way more of one than the other. On this side, we have a separate element, and we're going to do the same kind of calculations here. If I want to find the average atomic mass, I'm going to take the mass that they give me times the abundance plus the mass that they give me times the abundance divided by 100, or that same setup, but instead of dividing by 100, I'm going to move my decimal point 2 places. And no matter how you solve this one out, right, no matter where you put it, either top or bottom, you're going to get the same answer. And that answer is going to be 14.0067. All right, it doesn't matter if you plug it in this way or this way. As long as you do it correctly, both of these will result in the same answer. I have 2 more for us. And what I would like you to do is try to set these up. Right, I'm going to give you a minute and try to let you set these up. You don't have to plug them in, but set them up and see if you can get the setup correctly. And then we're going to go over them. So 1 minute on the clock. Go ahead and try this out. Okay, let's give this a shot. For this first one, we have again an exact weight and an abundance, so we have two different ways of setting it up. 34.968852 times 75.77 plus 36.965903 times 24.23 divided by 100, or 34.968852 times 0.7577 plus 36.965903 times 0.2423. And again, either way you set this up, you are going to arrive at the correct answer, which is 35.453. For this last one, instead of 2 isotopes, you have 3, which just means one more set of parentheses for you. So we're going to have 27.976927 times 92.23 plus 28.976495 times 4.67 plus 29.973770 times 3.10 divided by 100, or these same numbers, 27 times 0.9223 plus 28 all those numbers times 0.0467 plus 29 times all those numbers times 0.0310. And either way you set this one up, you are going to end up with the correct answer of 28.0855. And again, if we think about these mathematically, it makes a lot of sense. My highest value here is the 28, right? 27.9, being pulled upwards by two smaller abundances, but higher value. So my average is going to be very close to my 28. Here, mostly 35 with some 37 means it's going to pull me up a little bit, but my average is still closer to 35. Right? The abundance plays a big role in determining it. Just like in school, if you have a lot more hundreds than zeros, your grade is going to be higher. If you have a lot more zeros than hundreds, your grade is going to be lower. Right? The abundance of each grade, the abundance of each isotope, pulls the average towards it. And before we're done for today, I do have one multiple choice question for us. The atomic mass of an element is defined as the weighted average mass of that element's blank. So here, if we want to talk about the weighted average, right, the average atomic mass, and we want to make this akin to grades again. Let's go back to this example. You've got 4 100s and 1 0. Is your average, your class average, the average of that of your most abundant grade is your average 100. Your least abundant grade is your average a 0. Or is your average the weighted average of all of your grades? So an 80. And in this case, all grades make their way into the average. You don't just take the highest one and say that's your average. You don't just take the lowest one and say that's your average. You take all of the naturally occurring isotopes to make your average. And with that, we're going to transition our way over to our Google Meet for attendance and announcements, and I will see you all there.